I'm going to edit all of this into nice chunks so we can be a bit more informal. And if ever you want to just interject or stop, we have a lot more editing leniency this time. So thanks again, Karl, for joining us for another Ask Me Anything session. Very excited to have you on again. So I would like to know, I know you're going on vacation, as you usually do in August. So just before you launch into your vacation, what are the strands of research that you find most exciting, going into the summer?
Right. Well, at the moment, I am trying to rewrite in preparation for a book, the physics monograph. So at present, I have got slightly retrospectively seduced by trying to understand what I understood about 5 or 10 years ago.
Oh, interesting.
So literally, what have I been doing today? Trying to show that a certain and elemental kind of self-organization is an emergent property of self-evidencing or Bayesian mechanics, which is an interesting point of connection between the teleological or inferential interpretation or reading of the free energy principle and that which would be more favored by dynamical systems theorists, and in particular those people who like to think of self-organized criticality as something that sensitizes our brains to its sensory impressions. But I was trying to take a slightly less functionalist perspective and just join the dots between more principled accounts, and specifically the accounts due to people like Jaynes' maximum entropy principle, which of course is one half of free energy minimization. So if one remembers that free energy is equal to your expected or total energy minus your entropy, as you're decreasing the free energy, you are implicitly increasing the entropy. And what does that mean? Well, it basically means keeping your options open, generalizing Laplace's principle of indifference, which basically means the best kind of explanations for your content, data, or sensorium are those that have the largest conditional or posterior variance, or the smallest precision. So what would that look like in terms of dynamics? Well, if you work out the Jacobian of the flows, the gradient flows on a variational free energy, you can now link the eigenvalues of your posterior precision or uncertainty covariance to the Lyapunov exponents that describe the exponential divergence or convergence of trajectories. So I was trying to follow that through and try to tell a story that it is necessarily the case that if you've got the right kind of Bayesian beliefs about your data, then in virtue of Laplace's principle of indifference or Jaynes's maximum entropy principle, it must be the case that you are approaching criticality, that your Lyapunov exponents are approaching zero from below, and that has a whole range of interpretations. The ones I prefer are those that inherit from synergetics, where the system's divided into fast and slow modes, and these slow modes are the ones that are dynamically unstable, in the sense that the fast modes dissipate very, very quickly to usually a fixed point on technically a center manifold, or the set points prescribed by the slaving principle. So they're slow and unstable, they hang around for a long time, and they give rise to this kind of critical slowing, which is characteristic of one aspect of self-organized criticality. So there's a nice long answer. That's what I've been interested in today. Tomorrow it will change, depending on what's next.
Is your plan to re-edit a free energy principle for a particular physics and to maybe resubmit it, because that was the original manuscript that you had intended to submit to MIT Press originally, which then became the book that you wrote with Thomas and Giovanni, right?
Not quite. So you're absolutely right that the MIT Press were originally entertaining a proposal, and indeed that proposal was made after writing the physics monograph that was originally intended for peer-reviewed submission, but became too long. So it was put to MIT Press. And the then editor, Bob Pryor, who, if you remember, used to celebrate his name. He's in the beginning there were Pryors, and Pryors were good, and of course, he a priori had all the editorial rights to anything about Bayesian brains and the free energy principle. So he was a great character, now retired. So he'd been pestering me for 5, if not 10 years. And I kept saying, no, I'm not going to write a book. But then I had this monograph, which was almost bookish length. But of course, it was full of equations, and it was written for me. I wrote that for me as an autodidactic exercise, just to join the dots and make sure that there was an internal consistency between the formal arguments. It wasn't written for the readership of books from the MIT Press. So Bob very courteously ignored my emails for 2 to 3 years. So I was never rejected, but I was never received. And in the interim, Thomas and Giovanni wrote the active inference book, which is a completely different flavor. That was basically a primer, a tutorial, a demystifier, as much narrative as possible without worrying too much. Although they did a lovely job of sort of referring to the physics backstory, but it was not the physics backstory. And of course, from Bob Pryor's point of view, that was exactly what he wanted in the first place. So he made them put the free energy principle in the title, and then that became the active inference book, a free energy principle. So
Right.
blah, blah, blah. Leaving my monograph unpublished. But recently, Victor Gerso invited me to submit it to the Springer series on complexity. So I am now, so I'm now sort of bringing it up to date. Trying not to, in the spirit of being able to read the history, as a conservator, I'm trying not to change it too much, but to just note more recent references and to nuance a couple of points which were not expressed very clearly in the original manuscript. But it's taking a long time.
I can imagine. So, I mean, I want to stay on this for a little bit. I'm fascinated. So, what would you say has evolved in the last 6 years? I mean, I remember being at the Phil with you in January 2019 when we started going through the monograph for the first time. And it feels like we've come a really long way in the last 6 years since then. So at a high level, what do you think has changed? Did you spot any mistakes that you've fixed now? What is like the gist of the?
Well, I think there are two answers. My stock answer is nothing has changed. In the sense that you can actually go back before the particular physics monograph to a paper, I think written with Sengupta for the IEEE literature, which actually has all the fundamentals in it in terms of
with the gauge theory stuff, right?
No, this was actually before the gauge theory paper.
Oh, wow, okay.
And it was the first attempt to work exclusively in generalized quantum motion, which you would now know as the path-integral formulation. Link the Helmholtz-Hodge decomposition to the prediction and update terms in Bayesian filtering, and then to generalize that in the context of action along the lines of the original active inference papers in biological cybernetics. So the maths has been largely constant throughout. And this will be an opportunity. So I hope this is survives your edits. What has changed though is the easiest way to communicate. So
Mm,
it's fine knowing the equations, and sometimes I can write the equations and I've got no words to describe them, but they all make internal sense from my perspective,
mm,
which is useful in terms of um, the mathematical formal narrative, but useless in terms of allowing other people to apply anything that ensues from that kind of analysis. So the game then was to find the simplest way to communicate the ideas.
mm,
And then you're basically either taking your lead from established approaches, or indeed taking your lead from um, open questions that people are
mm,
interested in reading about, dumbing down to a certain extent, um, using words that people are familiar with. And one word I regret using is ergodic, because
right.
that's a whole series of deconstructions, misguided in my
Mm,
view, deconstructions of the free energy principle that were a symptom of the fact you were trying to find some way to communicate it without having to talk about path integral formulations, without having to talk about generalized quantities of motion, which are
mm,
still not, they're only implicit in the Bayesian filtering literature insofar as people use Kalman filtering. There are very few people who actually go the whole hog and use, use a full generalized quantities of motion formalism.
In
Um,
fairness, I think from the outside of the literature, sometimes it's difficult to identify what are core components of the formalism and what are auxiliary assumptions that we're making to basically allow us to, finesse the math a little bit. So, I mean, an example of this is, the Markov condition. You have a new paper out recently on, moving beyond Markov in transformer architectures, and even there's a sense in which the traditional kind of Markovian condition is a little bit modified when we're talking about the path integral formulation, for example. So it is kind of fair, I think, in some sense, that people have a little bit of difficulty keeping track of what the actual theory is, right?
Yes, I see. Well, actually, that is one, I think, useful example of something that has emerged as an important thing to communicate
Mm,
more recently, which is the implicit separation of temporal scales. So, of course, you
mm,
can't have anything that is ergodic in a system that has a separation of temporal scales, because at any scale you pick, there will be a scale above that
right.
has dynamics. And by definition, and certainly by appealing to the renormalization group, those dynamics will have a certain itinerancy. They will have a pullback attractor, which means by definition, at some point, there will be a beginning and end to anything below that.
Mm,
So, that's certainly been something which has been foregrounded, and it's been foregrounded in a number of different ways. From my perspective, in the context of evolutionary dynamics, the variational synthesis, where you've now got sort of the a variational formulation between bottom-up and top-down causation in evolutionary thinking or theoretical biology as an instance of this separation of temporal scales. It's been there before, early simulations of selection of neuronal elements on a dendrite appeal to the same kinds of
mm,
maths. And of course, you've got a natural link with Bayesian model selection, natural selection, which introduces the separation of temporal timescales. But to foreground that and to say out loud, this precludes any ergodicity or wide sense stationarity, um,
mm,
was not something that occurred to me that should be said at the beginning.
right.
Having said that, of course, if you go back to the monograph, chapter 4 of part 1 is all about the renormalization group and the separation of temporal scales. So it's
Right.
all, that's one of the foundations of the free energy principle. Yeah, there is certainly a Markov condition, or there is a Markovian universe at any given scale.
Mm,
That scale only exists, I mean, literally, in the way that states are, if you like, defined in terms of the blankets of particles, and particles constitute states. There's now a recursive definition of statehood that rests upon the renormalization group.
mm,
So, yes, at any one scale, you have these Markov boundaries, you have a minimal Markov blanket, at that scale that then induces the free energy principle and all its, and the basic mechanics that attends that. But the states that constitute the state space in which these conditional independences exist is itself transient, because it's just one part of one level or scale in the renormalization group, because the same laws apply to the scale above. So that's certainly something which has been a focus, of certain people. And one could submit that your work with Jeff and in terms of Markov blanket discovery is a nod in that direction, because the whole point of that work is that the Markov blankets can be in flux. So there is
an interesting thing is that the Markovian structure of the dependencies break down when you introduce the assignment variables that actually identify Markov blankets. So in order to identify Markov blankets, you have to step outside of basically the Markovian kind of world that you're simulating under the hood. And I guess that speaks to the scale specificity a lot of these simplifying assumptions that we're making. I mean, it strikes me that the same kind of story could be told about the non-equilibrium steady state assumption that was made, from 2012 to 2020. I think we all used that formulation. Yes. So, to say something exists at a steady state is to kind of zoom out in some sense and to look at it at a specific scale. But obviously, we all change. We have a beginning, a middle, and we all die, right? So it's a simplifying assumption that allows us to model and capture this kind of oscillatory behavior that living systems evince. But it's a simplifying assumption that applies at a specific scale.
Absolutely, yes, and I can remember years ago, you sort of smiling with pleasure when how did you phrase it, or how did we phrase it? We bring non-Markovian models to the table to model a Markovian universe, and of course that non-Markovian aspect is just what was entailed by the separation of temporal scales in any deep generative model that has this renormalizing aspect to it. So as soon as you have a separation of temporal scales, even in your deep generative model, recall papers like hierarchical timescales in the brain. This was a big thing a decade or so ago. And what that means is our generative models have a separation of temporal scales within them. And indeed, people in machine learning and now ourselves, we actually use renormalizing generative models. And of course, as soon as you do that, you've now broken the Markovian explanation. You've now gone non-Markovian, or as Dimitri would say, semi-Markovian. And yet, of course, the universe is Markovian at the scale that it is observed. At any given scale, it is Markovian. That's the whole point of starting the Langevin equation. So I remember you quite like that, that we have a non-Markovian models of a Markovian universe, which means that all that deep structure is something we bring to the table on the inside. When I was talking about ergodicity, I meant that synonymously with a non-equilibrium steady state.
Right.
And that was a big mistake, and originally to say that something has attains a non-equilibrium steady state after a year or so of people over interpreting that, we switched to saying has a non-equilibrium steady state solution. So what do you mean by that? It just means if you were able to integrate for t equals infinity, you would not get an exponential divergence, so that your states were now distributed throughout state space. It just meant that there was locally a solution that if you could integrate to t equals infinity, then you would have a pullback attractor, but never imagining that would actually ever occur. And of course, if you work in generalized quantum motion, you don't even need that assumption. You just need to know that there is a solution. It doesn't have to have a non-equilibrium steady state solution. So what I was trying to imply by using the word ergodicity or being ergodic was exactly the assumption that you need a non-equilibrium steady state to be obtained by something for it to exist. That's not the that wasn't the implication. The solution has to be there in order to derive the conditional dependencies from the coupling. So I think that's probably quite a fundamental thing as well, that sort of people have worried about, and has to be made, and has been the focus of work over the past few years, just to sort of nuance and expose the simplicity of being able to take dynamical coupling, true causality in a control theoretic sense, and say, if you know the adjacency matrix that underwrites your sparse coupling and your weakly mixing random dynamical system, then you also know the Markov blankets interpreted in terms of probability distributions. That's been quite an interesting sort of focus from a very technical point of view. It's not terribly interesting for most people, but for some people that's really quite interesting, just to get down into the weeds of that. But one interesting question that one might invite people to think about is, what is this probability distribution over? We've just got one state of the universe at any one point in time. We have not yet. We're still sort of pre-thermodynamics. There's not an ensemble. The universe is in this state at this point in time. So what's the probability distribution over? And of course, it is now over realizations in the future and possibly in the past. And that's where you need the solution to the equations of motion to actually have a non-equilibrium steady state in order to define that probability distribution. Otherwise, it doesn't exist. If there is no probability distribution.
These are basically the nuances that you want to add in the current version of the monograph before you publish it, correct?
In fact,
were they already there in some sense?
They were already implicit. So no, I don't recall. I haven't had to change anything of that nature. No. No, I'd say the only thing I've actually added is this sort of link to self-organized criticality, work done with Michael Breakspear and Gustavo Deco, just to sort of join the dots. So I'm just trying to think what else has been the focus. Oh, I have been able to reference your work with Jeff. I've been able to slip that in. So that's the kind of thing that I meant by bringing it up to date. So it's still reading history, but just to sort of get current. This just entails adding a reference here and there, or see this for a fuller discussion. Sorry. Just harping back to our previous conversation. So one reading of non-equilibrium steady state, the acronym, is a nearly ergodic steady state, which is why I sort of usually.
Oh, that's nice. I like that.
Use them synonymously. Yeah.
Well, very interesting. So, given all of this new work, well, let me actually. I think we've gone very deep on that first question. We've spent now like 25 minutes on the first question. Let me pull up a few questions that we got from the audience. It's been very. We've gotten a lot of very interesting ones. So taking this in another direction, so this is in reference to the newer inductive inference version of active inference, which in effect replaces the goal state that the goal that we previously specified in outcome space, now in state space. So I was wondering if we could explore that a little bit. The question is, are there practical benefits to minimizing uncertainty with respect to the hidden states rather than observations? What do you take to be like the main advantages of doing this? So I think we've talked previously about the idea that this better captures what we at least colloquially mean when we say that we intend to do something, right? when, at least colloquially, when we say that we intend to, achieve something, what we intend to achieve is not some configuration of sensory outcomes, but some state of the world. So I think just from a kind of commonsensical perspective, this is a sensible change in the formalism. But do you see any practical advantages? Is what the audience was asking.
Yeah, oh, it's a great question, and I think you've in part answered it. I think there are two ways to address this, and I think you've surfaced one of the key distinctions. So, inductive inference, by definition, applies to latent states or hidden states, as opposed to measurable or observed outcomes. And that, first of all, is that mathematically licensed? Yeah, if you just look at the various ways of deriving the expected free energy from the dynamics of self-organization under nearly ergodic steady-state solutions, then yeah, you're at liberty to switch them out, specifically in situations where your dynamics are precise because you're sufficiently big. You probably couldn't apply it to a mitochondria, but you could certainly apply it to a multi-celled organism or something like you and me. So usually in these situations, our dynamics are almost or nearly deterministic, and that basically means that the mutual information between all the partitions that constitute the Markov blanket partition are guaranteed for the person or the particle itself. So that means that what you can do is you can specify, for example, your risk, which is the divergence between what you anticipate if you do that and what you a priori prefer to happen, or the negative preference, the costs or constraints of certain outcomes. You can specify that either in hidden state space or in observable space. And of course, if you've got a likelihood mapping or operator or morphism, then just applying that to both sides of the KL divergence doesn't really change anything, provided there's no information loss on that likelihood mapping, which is why you're at liberty to specify stuff in latent state space versus outcomes. So I can well, perhaps I was going to say, I can imagine some people asking, well, why then have we always, in discrete state space formulations and possibly beyond, focused on the specification of risk in output space? The reason,
that's a fair question.
Yeah, and it is a question which I remember debating one of the very, very early sessions in the room that you were talking about before when we went through the monograph, with Danijar Hafner of Dreamer fame, and other things. And the reason for that is that in order to have latent states which are going to support your constraints or your prior preferences, you have to have a generative model. But if you're born into this world, if we take a biomimetic angle, without a generative model, because you haven't yet learned it, or you haven't acquired it, you haven't done your structure learning or Bayesian model selection, then there is no mechanism in order to house your constraints or prior preferences in the space of stuff you do not yet know. But you can be equipped at the point of creation or birth or prior to any Bayesian structure learning. You can be equipped with preferences that are specified in terms of on your Markov blanket. So if I said to you, look, what's the simplest specification of a self-organizing system? You'd say to me, okay, well, it's Markov blanket. Okay, we'll just think, what does that actually mean? Well, it basically means having some structure that determines or some description of some sensory states and some description of some active states, and that those descriptions have two bits to them. The first is the description of the sensory states now provides a support for you to specify the kinds of sensory states that this Markov blanket will encounter, and noting that there are lots of sensations it will never know. So you have to pick these sensory states quite carefully, and you also have to equip them with some prior preferences. So you are born effectively with an innate aversion to certain sensations.
Which we still have in the inductive inference version, right? Like we add constraints onto the
Oh yeah,
space of outcomes. So you still can have something like I'm
oh yeah.
averse to, detecting high temperature on, my skin or something like that.
No, absolutely. Yeah, that's the second answer, where there's the second part of the answer, which is a practical advantage of the inductive. I was just trying to make the point that um, when you think about where constraints are specified from an evolutionary perspective, for example, from a practical, if you have to have a child or make a machine, then you would have to specify it in terms of the outcomes, in terms of priors over the sensory sector of your blankets. And I also just wanted to add that you also have to specify the reflexes. So that's not part of the generative model. It's, you have to give it a body, and the body entails certain states of the sensory sector being viable, or there, and also the relationship between the active and the sensory sector, which of course will be mediated via the external states. That's basically, you have to be given reflexes. You have to be equipped, born with reflexes, but they're all expressed within the Markov blanket. You don't need a generative model underneath the Markov blanket to do that. But if you're now old and wise and you've learned a generative model, now mathematically you can now acquire and learn preferences over your hidden states, as we all do. And I think what you said before was very important. I think that, at least in the vernacular, or colloquially, now we have intentions. But these intentions, we're not born with these intentions. Almost by definition, we have to acquire a world model in which we can learn what are the kinds of states I intend to work towards. And so these inductive, the constraints that underwrite inductive inference have to be learned or installed or taught. And I think you're absolutely right. They're much more intentional in nature than the more merely reflexive specification, or the specification of outcomes that underwrites merely reflexive active inference. But practically, you also make the point that the way that inductive inference works, it's not, it works in negative. It's one of Dan Dennett's strange inversions. What it says is, if I intend to be in one of these hidden states in the future, and I've now got a sufficiently precise generative model that entails all the dynamics or the transition probabilities, I now know all the allowable transitions or paths that I could pursue. And if I know that, I can do a very simple form of backwards induction. I can start from all the states that I think I intend, all the states that I intend to be in, and then propagate them back in time. And what that does is, if I allow for that propagation to accommodate all allowable transitions, it basically tells me, it splits the next state into two groups. One group of states, if I go down any one of these, there is an allowable path to an intended state. But there's a whole other universe of other states that have not been connected to my, through time, backwards in time, to my intended states. So if I go there, I know that I can't get to my intended state. So what that does is it gives you another constraint. It just gives you a constraint that takes all of those transitions off the table. So now you're left with a whole bunch, a set of next states, all of which there is an allowable path to my intended states. And then you just apply the normal expected free energy, the normal either sophisticated or vanilla active inference to pick within the remaining states that have not been excluded by this kind of backwards induction. So that's exactly right. Your inductive inference is not a replacement for vanilla sophisticated inference or active, unsophisticated or vanilla active inference. It's not a replacement for the expected free energy. it provides a really useful constraint on the expected free energy. That means that you can now you can think of your intentions as constraints on working towards your either epistemic or instrumental goals that could indeed, as you say, be in and generally are in output space. The practical advantage of this is that you're working with constraints, and these constraints are only available if you have very precise beliefs about the dynamics. But we've just said that we are only applying this kind of intentional inference to old wise things that have now learned very, very precise dynamics in their world model. Because these dynamics are precise, you can get a long way into the future. So in contrast, if you are very young and you haven't really worked out with any degree of certainty all your transition dynamics, as soon as you start rolling out into the future by 1, 2, 3, or 4 more time steps, the uncertainty just accumulates. And because your certainty accumulates, your expected cost and your expected information gain all become level playing fields across all the policies. So there's no point in doing a deep tree search if you've got imprecise beliefs about the future. But if you're old and wise and you can have intentions that have been accrued through lots of experience, you can get a long way out into the future, and you can sort of emulate that mathematically by just thresholding your probability transition tensors and marginalizing over all allowable actions to get the allowable ones and convert them into logical matrices. And once you've got these logical matrices, you can do hundreds and thousands of iterations out into the future and back again, which are all very, very precise. So that means within a few milliseconds, you can actually do deep trees, effectively do deep tree searches. But I repeat, these are not searches for the best outcome. They are searches for where not to go.
Right.
So the practical advantage basically is that you can now look 64 steps into the future, and then triage a whole bunch of options, and then just use your sophisticated inference for 1 or 2 steps into the future in that which remains. So it massively increases the efficiency of long-term forecast or what you long horizon kinds of planning.
So thinking a bit laterally, would you relate this at all to the notion of sensory self-attenuation in the more continuous formulations? It occurs to me that at least conceptually there is a parallel between having very confident beliefs in what I'm trying to achieve on the one hand, as you would in, for example, the active inference models of motor preparedness and generation of action, and what you just described here with inductive inference. Or am I reading into that too much?
Well, I don't want to say you're reading into it too much. I think what you're picking up, though, is the potential importance of having very precise beliefs that enable you to do a kind of categorical selection, and certainly sensory attenuation and indeed attentional selection would be a good example of that. That I'm now doing mental action, for example, by selecting this likelihood mapping, or given that now all the other contenders have near zero probability. So I think you see that a lot, and that's certainly, as you know, an emerging theme in machine learning, artificial intelligence research. You could indeed argue that the very existence of attention heads in transformers is a simple example of this, that is necessary to get this notion of selecting the most likely token that has a predictive validity in relation to the next token. So this is learning how to attend. So you've got that kind of attentional selection there. that is, it's not quite discretized, but it's certainly, if you like, that selectional aspect rests upon the softmax or the sigmoid operators that are generally used to convert logic representations into or to do the selection, very much in the spirit that one would select policies in the context of inductive inference. However, I think sort of attention and attenuation as really important capacities for many ways of reading this. You could say it's Bayesian model selection, you could say it's slot attention, you could say it's attentional selection. That applies everywhere, not just to your planning and your policies. I think in many respects that the policies that prescribe certain attentional plans, certain mental actions, probably supervene on the deployment of attention. But you can still have attentional mechanisms without necessarily invoking them intentionally. But if you want to now simulate, and this is the argument for phenomenology from many people, including, or in particular, people like Lars Sandved Smith and his colleagues, that you have to volitionally intend to attend to something before it acquires a certain opacity. And by volitional in this instance, not only do you have to engage in inductive inference to realize the intention to attend or selectively attend to this modality or this source of evidence, but you also have to model yourself doing this. I think they've got up to about 3 levels before you get to any sort of volitional or propositional kind of intention. And then, of course, you've got Rubin and Shamil, who have now introduced their beautiful loop, which is another, if you like, expression of this sort of internal action, where the highest level or the inner screen knows itself through acting on everything else below through these attentional mechanisms.
That's beautiful, and it segues nicely. So we have 10 minutes left on our scheduled time, and I want to respect your time. So your comments about phenomenology segue nicely into the last question I wanted to ask you today, which pertains to, I imagine you've been invited to comment on this. So Anil Seth wrote a recent paper on artificial consciousness and biological naturalism, which I suspect you've been invited to comment on, and several of us have been as well. I've been thinking about this recently, and I wanted to pick your brain on this. So the essence of my commentary says something like, we need to guard ourselves from making an inference from the availability of a computational model to the idea that what is being modeled with that model is itself engaging in computations. So for instance, the fact that we have a computational model of the orbit of Jupiter around the sun does not entail that Jupiter itself is taking an integral. And my question to you has to do with the availability of computational models of consciousness and the inference that some people are making from the availability of these models to maybe the worry that, hey, these models themselves are conscious, and now we need to worry about the welfare of these systems. Like, are we snuffing out a sentience when we shut off our computer for the day when it was running an active inference consciousness model? So I was curious what your thoughts were about that. Are we close to accidentally creating conscious artifacts and inducing a bunch of unwanted suffering, or is this sort of like you wouldn't expect to get wet from simulating the ocean, and similarly you shouldn't worry about offending something that seems to be responsive but probably isn't?
Yeah. We could talk for hours about any of those multiple directions that you mentioned there. I think probably I'll just make 2 points. One, a brief point, and then about sort of artificial consciousness, and then the specific take that you introduced on Anil's sort of biomimetic natural focus. There is an argument that I'm quite happy to subscribe to, but it's not my argument, and that we actually do need to build consciousness or sentience into artificial intelligence for our collective safety. By collective, I mean both the artificial and the natural intelligences. So this is, I would imagine, would be Yosha Bach's position. It's certainly the lead on the California Institute of Machine Consciousness. That's basically
It's very cool what they're doing.
Yeah, and so it's a slightly counterintuitive position. It's saying, let's, almost saying, do not, don't worry about the doomerism and machine welfare. That's not the point. The point is we need artificial consciousness to be able to engage with in a bilateral and empathetic way artifacts that are not natural or man-made, that have who want to participate in this ecosystem, because without that there will be no evidence that they are doing true inference, by which I mean that they've got the right objective function, and by the right objective function they fit into this ecosystem in virtue of maximizing the marginal likelihood or minimizing the variational free energy. The literally adaptive fitness is scored by the likelihood of their interactions, their exchanges on the web, through their Markov blanket or through their input-output or interface with the user and other machines. So if you want evidence that you're using the right objective function as opposed to a human crafted, possibly bad actor specifier of a reward function, then you're looking for evidence that they're using the right, your artifact's using the right reward function, which means it should show some kind of self-evidencing, which means it should ultimately start to become more like you and want to know about you. So that would be a sort of paradoxical pushback against the doomerism of machine welfare. I'm not saying it's right. I'm just saying that there is that other argument, which is actually, slightly easier to argue from a sort of mathematical perspective, in terms of.
Yeah, I'll have a question about that, but I want to hear the other argument first.
Right. Well, the other one's much simpler. It's so I read much of Anil's paper as the problem of simulating consciousness on a on something that was not at least biomimetic, if not neuromorphic. So I thought his argument was that consciousness cannot be, and perhaps it fits with your functionalist or computational argument. So if you have the ability to compute or calculate in the sense that you were talking about the orbits of Jupiter, you're talking about immortal computation. You can reproduce that either on a computer or with pen and paper anywhere. That idea, that maths, that kind of computation lives forever. It's substrate independent. I thought Anil's argument was then that you cannot be conscious if you're ascribing consciousness as an attribute of immortal computation. It has to be mortal. It has to be lived. It has to be substrate dependent, and all the implications of that basically are that what's the bright line on the difference between mortal computation and immortal computation, and then he goes on about efficiency and the thermodynamics. So my brief was to look at the thermodynamics. And of course, the difference between, the difference between, well, the brief I took, although I also suspect that's what he wanted me to do, was to sort of compare and contrast artificial intelligence as we currently know it with the thermodynamics of mortal computation. And then we get into the usual arguments, which you could, well, and perhaps you should do that. We can do that next time in terms of sort of, the Landauer's principle and the Jinsky equality, providing a bound on the thermodynamic cost of belief updating. But that argument practically gets unpacked in terms of, well, yeah, that's all very nice, but those lower bounds, those Landauer bounds on the thermodynamics of belief updating, just evaporate into trivia when you're looking at the amount of energy it costs to run a von Neumann architecture, reading and writing to memory. So
Well,
the big
precisely.
time,
Absolutely.
yeah,
I mean, in some sense, digital, like classical computing architectures and quantum computing architectures are very bizarre artifacts that are basically built to be frozen. Whereas if you think of learning, almost every other system that learns in a kind of continuous way through energy dissipation, effectively. So there's a sense in which we create these rigid, immortal computers that are very unlike anything else. And I think that does create a strong disanalogy between the kinds of things that do live and make sense of the world, and these these artifacts that we then use as analogies to understand the actual natural intelligence of things. um to just kind of circle back on the first. Oh, did you want to add anything to that?
no, as I
Okay.
said, there's too much to answer.
Yeah,
Let's
we could probably focus that on the next set of questions. Um, just on the first point that
what
you
you could
made.
do is invite Neil and pose these questions to him as
Oh,
well.
that's a fantastic idea. That's a great idea. Okay, that's what I'll plan to do for next time. But yeah, I wanted to just in the 1 minute just address the first argument that you made. I guess what worries me about appeals to machine empathy is, I mean, I totally take the point that things that act empathetically in the natural world are sentient, and that we would probably have difficulty being empathetic if we did not have this kind of sentience. But I also note that the only things in the universe that we know to be malicious are also sentient. So I think that's kind of a toss-up. I don't know if designing an artifact and endowing it with some form of sentience is in itself a safeguard against malicious behavior. I could see it go both ways, actually.
Yes, no, that's a good point. Yeah, yeah, from my perspective, it's more about writing down the appropriate objective function. So, when you're building stuff, perhaps we just go back to the free energy principle and remind ourselves that the free energy principle is just a description of the way things are, where things are carefully defined in terms of the Markov blankets.
Right.
That in and of itself doesn't tell you anything. You can just say, oh, I'm here because of natural selection, and go home. So the free energy principle in and of itself doesn't do any hard work at all.
Right.
However, what it does do is give you a mechanics that allows you to write down the thing in terms of a generative model and then solve it by applying the Feynman trick of converting an impossible marginalization problem into optimization problem. So what that means is that you can use the free energy principle to apply optimization, basically a gradient flow on variation free energy, to create things. And by things, I mean things that exist in some sustainable way.
But wouldn't you say that it's just as important to define the right model than it is to define the right objective function? I actually was discussing this with Guillaume Verdon last week, who's the CEO of Extropic Corp, the thermodynamic chip company, and we were discussing whether the mere fact that a system well, the question is, does the mere fact that a system minimizes free energy guarantee anything with respect to its ethical makeup? And Axel Constant and I have been
Yeah.
arguing about this for years, and I think if the free energy principle holds, then there are all sorts of horrible social configurations that exist and therefore must minimize free energy. So presumably, a totalitarian autocracy is also a free energy minimizing
Yes,
device.
I
So
think I think you do have to accept that, and yeah, I think I would imagine your exchanges that's all very revealing and engaging, but you will certainly have to accept that. So if my more polemic point here is that you've got to stop people using reinforcement learning in the sense that
right,
they are now in charge of the constraints and the reward function. That's the danger. You can easily get bad actors to
right.
militarize and weaponize um, you know artificial intelligence to do all sorts of things if you allow them to use reinforcement learning to reward the behavior they think is should be optimized. What I'm saying is that if you um, if you use the variational bound as the objective function, then you will create things that do adapt their environment. And they will exist in the sense that they will persevere for us and they will be sustainable. Let's use that word as
Right.
a nearly ergodic steady state solution. And the nature of that existence may not be so intuitive. You're absolutely right. Autocracies are extremely functional and enduring forms of social organization. And if I
There's
was
very
living,
little entropy in a
yeah,
ethnically
and
homogenous group, right?
if we weren't talking as an Englishman to a Canadian, I could say that the real danger is dollars and democracy. That's not a stable, sustainable way of running a
Right.
society. So I wouldn't assume autocracies are, from the point of view of the free energy principle, really bad things. Very much in the spirit that dying is not a bad thing; it's just part of a life cycle. It's sustainable.
Right.
So it implies reproduction, replication. So yes, you're right. There could well be wars, but wars in and of themselves are things that are characteristic of the itinerant dynamics of our biosphere and our social ecosystem. So things that may be unethical on one level are still perfectly viable solutions, free energy minimizing solutions. Then you have to ask yourself, well, they're not very, they're quite surprising for me to be in a war zone. Yeah, absolutely. So then you have to think about the mechanics of this ecosystem. But at least this ecosystem is sustainable.
Right.
What we're talking about is something that is not sustainable. For example, the doomerism of climate change.
Mm.
That would be accelerated by a non-judicious use of electricity to fuel data warehouses,
Right.
petroleum cars. Now, it may not happen, but you could, some climate modelers may actually say, well, look, if we don't change course soon, uh, there will be, the termination of this particular lifetime of this particular species, humanity, um, and that would be the end of that nearly ergodic steady state.
Right.
So, or we could have wars, which seems to sort of fuel the economy and and have this cyclical aspect, boom and bust aspect that is more sustainable. So I think the ethical questions there are probably you're probably using ethics and morality in a much more informed and philosophical sense. From a maths sense, all we're interested in is sustainability and persistence.
Well, that's why I was saying. That's why I was referring. I think the way I would cash out these ethical distinctions is saying that we're not using the same generative model. Basically, we're not minimizing free energy under the same generative model. If we
I
have
see. Yeah.
an ethical distinction. Well, I mean, to your point, Karl, I think we could probably talk about this for another couple hours. So I'll save this as a kind of focused topic for the next Ask Me Anything session. I mean, in the meantime, I hope you have a graceful segue into your vacation and that you have a great month off. It's definitely well deserved. So thanks again for joining us for another awesome conversation. And I'm looking forward to the next one.
Brilliant. So am I.
Excellent. So
Bye-bye.
I'll cut the recording now. So thank you very much, Karl.